DeepSeek just dropped something they're calling a 6 times speed boost for AI, and the internet went a little crazy over it. The claim is wild. Your models answer up to 85% faster with zero loss in quality. No smaller model, no dumber answers, just faster. And normally, when someone promises free speed with no downside, that's exactly when you should get suspicious. So I didn't just read the paper, I installed it, I ran it on my own laptop, and I timed it myself. And what I found is more interesting than the headline because it's real, but the 6 times number is hiding something they're not putting in the thumbnail. Let me show you. So here's what actually happened. DeepSeek open sourced a framework called DSpark. It lives inside their DeepSpec project on GitHub and it's MIT licensed, which means anyone can take it and use it for free, even commercially. That part is genuinely a big deal. It isn't a locked API you have to pay per token for. It's the actual technique in the open that you can run yourself. And the technique has a name that sounds scarier than it is. Speculative decoding. Don't let the word scare you off because the idea is beautifully simple. And once you get it, you'll see why it works and why it sometimes doesn't. Here's the problem it solves. A big language model generates text one token at a time. Token, then the next token, then the next. And every single token means running the entire massive model again from top to bottom. That's why big models feel slow. It's not thinking hard, just that each word costs one full pass through a giant network. Now, here's the clever part. What if you had a tiny, fast model, a little assistant that runs ahead and guesses the next few tokens? It's cheap, so it's quick. Then the big model doesn't generate those tokens one by one. It just checks the little model's guesses all at once in a single pass. If the guesses were right, you got 4 or 5 tokens for the price of one. If they were wrong, you throw them away and the big model takes over. You never lose quality because the big model always has the final say. You only ever gain speed when the guesses are good. DeepSeek calls the little guesser a draft model or a scout. The big one verifies. That's the whole trick. A scout runs ahead, the boss confirms, and when the scout is right a lot, you fly. So what does DeepSeek actually report? On their V4 Flash model, they measured 60 to 85% faster generation per user. On the bigger V4 Pro, 57 to 78%. And they talk about roughly 6 times the output capacity when you add it all up across many users at once. Those are their numbers from their paper on their hardware. I want to be clear about that. I'm citing them, not claiming them, because the real question isn't, did DeepSeek get 85%? The real question is, will you, will I, on a normal machine with a normal model? That's the video. Here's my setup, and I kept it honest and simple. I'm on a MacBook, an M4 Pro with 24 gigabytes of memory, no GPU cluster, no cloud. I'm using MLX, Apple's framework, which has speculative decoding built right in. You just point it at a draft model and it does the rest. Now, DSpark's draft models are trained specifically for the Qwen family and Google's Gemma. So I used Qwen 3 as my big model and a tiny Qwen 3, the 600 million parameter version, as my scout. Same prompt every time. Write me a binary search tree in Python. Same length, same settings, temperature 0, so it's repeatable. The only thing I'm changing is scout on or scout off, and I'm watching one number, tokens per second. Higher is faster. Let's run it. First test. My big model is the 4 billion parameter Qwen. I run it normally, no scout, 82 tokens per second, fast. Now I turn the scout on, the little model runs ahead, the big one verifies, same prompt, and 58 tokens per second. Wait, that's slower. Adding the speed trick made it almost 30% slower. That's the opposite of what the thumbnail promised. And this is the exact moment most videos would quietly not show you. But this is the most important result in the whole test because it tells you when this trick fails. Why? Because it's the key to the entire thing. Remember, the scout isn't free. Running that little model to make guesses costs a little time, and checking the guesses costs a little time. So there's overhead. Speculative decoding only wins when the time you save by skipping the big model's one at a time grind is bigger than the overhead you added. But my 4 billion model was already fast, it's small, it doesn't grind. So there was barely any slowness to save, and the scouts overhead just ate the difference. You paid for a helper you didn't need. That's the catch. On a small, fast model, this trick is dead weight. Second reason it went backwards, and it's subtle. My scout and my big model don't always agree. Every time the scout guesses a token the big model wouldn't have picked, that guess gets rejected, and everything after it in that little chain gets thrown out too. So you did the work of guessing, plus the work of checking, plus the work of the big model taking over anyway. On a small model where you weren't saving much to begin with, those rejections push you straight into the red. Speed, quality, overhead, you only win when all three line up in your favor, which raises the obvious question: what happens when the big model is actually big and slow? The kind of model that does grind. That's where it should shine. So let's scale up. Second test. Now my big model is the 8 billion Quen, double the size, noticeably slower on its own. Baseline, no scout, 44 tokens per second. You can feel it's heavier than the 4 billion. Now I turn the scout back on. Same little 600 million guesser, same prompt. And this time, 50 tokens per second. Faster, about 13.5% faster for free, no quality loss, just by letting a tiny model run ahead. There it is. The trick works. On a real machine, on a model people actually use with nothing but open source code. And notice what changed? Nothing about the trick changed. Only thing that changed was the size of the big model. Small model, slower, bigger model, faster. That's not random. That's the whole pattern. There's one more thing I learned, and it matters if you try this yourself. There's a setting, how many tokens the scout guesses at a time. I had it at 3, and that gave me the 13% win. Out of curiosity, I pushed it to 5, let the scout guess more each round, and it got slower again. 39 tokens per second. Why? Because the more the scout guesses, the more likely it is to be wrong somewhere in that chain, and one wrong guess throws away everything after it. Guess too little and you barely save anything. Guess too much and you waste work on rejects. There's a sweet spot in the middle and you have to find it for your models. This isn't plug and play magic, it's an engineering dial. Now let's connect my little laptop to DeepSeek's giant claim. Watch this curve. On my 4 billion model, the trick was negative. It cost me speed. On my 8 billion model, it turned positive plus 13%. See the direction? The bigger and slower the model, the more this trick pays off because there's more grinding to skip. Now extend that line all the way up to DeepSeek's V4, a model with around 1 trillion parameters. That thing is enormously slow per token. It grinds like nothing I can run on a laptop. So the room to save is massive. And that's why they measure 60, 85%, not 13. Their 85% and my 13% are the same trick. The only difference is the size of the model underneath it. It was never a magic number. Always a scaling curve, and they're sitting at the top of it. There are two more reasons their number beats mine, and they're worth knowing. First, memory. When I tried to jump to a 14 billion model, my Mac ran out of headroom. Holding the big model and the Scout at once choked 24 gigabytes, and everything slowed to a crawl. Seek runs on data center GPUs with room to spare. Speculative decoding is hungry for memory because you're running two models at once. Second, and this is the real secret, their Scout is trained. I used a generic small model as my guesser. DeepSeek trained a custom draft model to imitate the big one, so its guesses get accepted way more often. Higher acceptance means more free tokens, means more speed. That trained scout is most of the magic, and it's the part you can't fake with an off-the-shelf model. Let me make this practical. If you're running big models locally or serving them to lots of people, this is a real free, no downside speed up, and you should turn it on. If you're on small, fast models, don't bother, you'll go backwards. If you want DeepSeek's headline numbers, you need three things together: a genuinely big model, enough memory to hold two models at once, and a draft model trained to match. Get all three and 85% is real. Miss one and you're in my 13% world, or worse, my negative world. And honestly, That's the part I love about actually testing these claims instead of just reacting to them. The headline was clickbait. The engineering underneath it is real, elegant, and genuinely useful. You just have to know when it applies. Now you do. So that's DSpark, a beautiful trick, an honest catch, and a number that only makes sense once you understand the curve. If you want to go deeper on this stuff, building with AI agents, testing these tools yourself, turning this into an actual business, check out our community in the description down below. That's where we go hands on with all of it together. And if you liked watching me put a viral AI claim on the clock and get the real number, check out this video right here where I fixed one of Claude Code's biggest problems live. Click it on the screen right now, and I'll see you in the next one.